This is just a really brief video to introduce some of the differences between correlation and regression. Often these two things can be confused together simply because correlation really does drive into regression, and trying to see how regression adds is sometimes a little confusing. So both correlation and regression are both deal in correlation. So we have four options here. Correlation examines the linear relationships between two variables. That's it. All that can happen when we deal with correlation data is we can have a positive relationship, in which case when we have a positive relationship we start to see a trend of as x increases, y increases. So this is a positive relationship. We could have a negative relationship where you generally see a trend where as x increases, y is decreasing. You could have no relationship. So in no relationship, you just sort of see a scatter of dots all over the place, but no upward or downward trend. So this would be no relationship. And then you could have a curvilinear relationship. Now, correlation can't handle, as we discussed in class, correlation can't handle a curvilinear relationship. It underestimates it and usually calls it no relationship. So that's correlation, and correlation can deal with direction, which is what I present here, and it can deal with strength. So that's where we've talked about how it can go from, it'll deal with absolute values where less than 0.3 is considered a weak correlation, between 0.3 and 0.6 is considered strong, or medium or moderate correlation, and above 0.6 is considered a strong correlation. Remember, these are all reported in absolute values because it doesn't matter if we have a positive or a negative correlation. That's still the case. So regression now takes that information of the linear correlation and starts to develop a linear prediction of y by x. So it starts the same way that we see a xy correlation start, and that's with a scatter plot. So we have a scatter plot of all these dots, and we're starting to see a positive trend get visualized here. It's probably a relatively strong positive trend based on the way I'm drawing it. And then, using the sum of least squares principle, a single line is developed. Excuse me, I'm having problems with my stylus. A single line is developed that tries to limit the error between the prediction line and any of these dots. So the distance between the line and this dot and the distance between the line and this dot are attempted to be limited, and it's the total, or we try to minimize the total variability within the whole sample. When that line's drawn, we get two pieces of information. We get then A, which refers to the y-intercept, and we get a B, which refers to the slope. Sorry, my stylus keeps turning off on me. So we get B, which refers to a slope. Y-intercept is simply the value of y when x equals 0. The slope is that rise over run, or it's the change in y for a 1 unit change in x. This information is put together to create a prediction formula where y predicted is A, or the y-intercept, plus B, the slope, times some x value. Now, here's pretty much the major differences. The basic assumptions for correlation and regression start in the same way, in that we both need interval or ratio variables in both, for both our predictor and our criterion variables. Regression will eventually need more, especially as we move up into the multiple regression. And that has to do with fairly large sample sizes. It also has to do with making sure that the correlations between predictors is not too high. We call that collinearity. That's not something we're going to talk about too much in this class. We also start to look at, we have to make sure, of course, that we have normality of our variables, and so on. So the basic assumptions are just more for regression than they are for correlation. In terms of significance testing in correlation, we have that just one test. Is that p-value have an associated alpha, or is the p-value for r less than 0.05? In regression, we have a couple of different tests. First, we use an f-test to test the model, and we get a p-value there. And then we do t-tests to test the predictors, and we get another p-value there. So in correlation, we do this. Is there a significant linear relationship? If without that piece of information, we really could not do this next component. You need this component to be accurate. A correlation, you need to meet that requirement in order to even do the f-test or the t-test. You can't actually do it the other way. Or you can't, if something doesn't correlate, it won't significantly predict. In terms of meaningful significance, now that tends to be relatively, or again, has a lot of similarities. Both of them can look at a variable called r. Both of them can square it to get explained variance, so we can get r squared. So we can have the correlation, and we can have the coefficient of determination in both correlation and regression. In regression, we have a few extra ones. We have the standard error of the estimate, which is the standard deviation of the regression line. We have 95% confidence intervals, both of the slopes of the predictors and of the regression line as a whole. We also have that r squared value. And then there are additional, when I get into my higher doc stats level correlations, there are some incremental partitionings, some of the smaller correlations, things like semi-partial correlations and partial correlations, well beyond this course. Now, because regression is based in correlation, everything that we identified as a limitation to correlation is a limitation to regression. So when we identified that there was no cause and effect in correlation, that meant there is also no cause and effect in regression. Similarly, the sensitivity to sample size, divergent groups, restricted range, and why am I now blanking on another one? Causality, sample size, divergent range, divergent groups, restricted range. Oh, I'm blanking. But all of the limitations that apply to correlation are going to therefore apply to regression, because again, it goes back to this additional or early basic assumption. You do not put something into regression if they don't significantly correlate. So to just kind of finish off this table, everything that's over here is specific to regression. Everything that's over to the left is correlation and regression. So they both are, regression kind of has everything that's based on correlation plus some things. There's a lot of information in this one. Some of it really doesn't apply to the 620 class, but some of it should at least give you just some highlights into how we can get much more information out of a regression equation than just the basic information of intensity and direction that we get out of correlation analysis.